ciphertexts, or sometimes even with more strategic way, not really random. It really depends on the type of the adversary. And then the adversary would send the ciphertext, and the only thing that the crypto system would check is that if this ciphertext that the attacker is querying, it shouldn't be equal to a challenge, because if you answer the responses to the challenge, then, well, it is already revealed the answer to this challenge, right? It wouldn't make sense. So the or algorithm would make sure that they can query about any ciphertext except for the one that they are the crypto system has chosen as a challenge, and then they would return the corresponding message for every query that or adversary would make. And then at the end, adversary would probably craft in some specific queries so that it would help him to reveal the message. At the end, the adversary would answer and says that, the answer to this challenge C is MS star, and he would win if MS star equals to N. For the case of the RSA, we've seen that we set up the adversary in the same way. We just call him Eve, and then we said that it is very easy to attack the RSA. So as soon as Eve received this challenge, he would randomly choose the R from the set of Z star N. He chooses Z star N because the inverse of this R exists. Later we need this for division. And then he would do this computation. He multiplies C to the R to the E. Where E comes from? E is the public key of this crypto system and is publicly available. So definitely he can do this computation. And then he would send the C prime to RSA and ask him, can you decrypt this one for me? So of course this C prime is not equal to C, and RSA would say, okay, you're asking for some other ciphertext than the challenge, and of course we would decrypt it for him, and then he would get the M prime, and all he has to do based on this computation is to divide M prime by R, and then that's where he would get the answer to this challenge. So the textbook version of RSA is completely insecure against this attack. And this kind of attack, unfortunately, happened in real world. For the best practice, we always suggest to use some crypto systems that are secure against the CCA attacks, because this could happen quite often when you really use this kind of crypto system in practice. So for that, we have seen that somehow, we've seen when we design this sort of games, we have our crypto system to answer some of these challenges. So sometimes the party or the section that answered to these questions or these queries is what we call it Oracle. So Oracle, we said that is a very powerful object that can do things in a unit time. That means that it is not even a polynomial time. It is just like unit time. It takes no time to get the answer. For example, we show you that we have decryption Oracle, just like what we show in this example, that when you send the ciphertext, you will be able to answer to decrypt the message. And sometimes we also talk about signing Oracle. That is signing Oracle, whatever message we send, the signing Oracle would help us to get the signature for it. Sometimes we call it hash Oracle. When you send a message, the Oracle would compute the hash of this message for us, and so on and so forth. There would be many different examples out there. So I think we have one more attack to discuss about the RSA. And right after that, we are going to see that if it is possible right now that we've seen that RSA is not secure against CCA attack, we are going to explore and see if there is a way that we can protect RSA against this attack. So that would be the subject that we are going to mainly discuss today. So regarding the remaining attacks on RSA, there are two more things that we need to make sure. One is that when you choose a prime P and Q, so the P minus 1 and P plus 1 should have a large factor R and R prime. And also, the R minus 1 itself should also have a large prime factor. So these are just, some magics that happen when you choose a sort of insecure prime. Sometimes it is possible to run some specific attacks. Again, this is another advice that you always use these libraries, famous libraries, for utilizing RSA in practice, because when you use, for example, OpenSSL, when you generate the prime, they would go and do all these checks for you and make sure that the prime that you have chosen is safe. So you don't have to worry about this. But some of these attacks we just discuss over here because they are very interesting for you to learn some techniques from them. The other one that I actually want to discuss a little bit further is the second attack over here. This is a little bit more interesting. So what it says is that it should happen that when you choose a P and Q, then the difference between P and Q must be large. What does that mean? That means that the P and Q that you choose, roughly you choose, for example, for RSA of 1024-bit N, you choose two prime numbers P and Q, which are roughly 512 bits. Because when you multiply two numbers that are 512 bits, the resulting N is going to be around 1024 bits. So there is a situation here that it says that the P and Q should not be very close to each other. In what happens if they are close, then it means that the number of the bits in Q and P and Q should be significantly different, right? So let me write this down. The number of bits in P and Q are significantly different, right? When they are close, for example, look at this example. For example, 1010 is in binary, is the binary representation of the value 10, and this is 10. And if you choose another number, for example, 11, let's say, it is going to be 1011, right? So this is the binary representation. When these two numbers are close to each other, the other way around to see them is that their bits are quite the same, right? If you look at them 1, 0, 1, and then only the last bit is different. So the number of the bits that are in there should be significantly different. That is another way in binary format to see them. So that is not the point. So the point is there is an attack, and if this is the case that you choose P and Q to be very close to each other, we can factor N. That's what we are going to show. So the whole thing starts with here, that if P and Q are close, then P minus Q to the 2 over 4 is also small. So because this thing is small, if you square something small, you won't really increase it much. So in that note, let me start with some equation. So I don't want you to see this whole giant formulas and get confused. So the whole thing starts with a formula called x to the 2 minus n. Okay, just remember this one equals to y squared. So let's see what do we mean by that. So if I happen to have P and Q, then I can say that P plus Q divided by 2 to the power 2 minus n. Let me expand this formula. So far, I don't have a knowledge of P and Q, but we would see that supposedly we know that P and Q. Let's see what we can do with it, and then we see that what heuristic algorithm we can develop to extract this P and Q. So let's just expand this formula. So in the denominator I get 4, and then over here I get P to the 2 plus 2PQ plus Q squared, right? And then n, we know that it is p times q, so it's just going to be minus pq. So let's expand this one. I get 4, and then p to the 2. If I get this one up there, so I get minus 2pq plus q2, and what I get is 4, and then over here I would have p minus q to the 2, right? Which I can represent this one as p minus q over 2 to the power 2, right? These are all equalities. So I start with just p plus q over 2 to the power 2 minus n, and I just expand this one, and I got this to be equal to this value. So all we are trying to say is that we said that if this p and q are close to each other, if you square them and divide them by 4, that would also remain relatively small because the difference between these two numbers is small. So remember, you see that what we've got over here. So this equality is going to be a small. So, and then how did we get here? We just expand this formula over here, and then that's how we got ourselves over here. And now this becomes a little bit interesting. And what does this mean is that the difference between this p plus q over 2 to the power 2 minus n should be small, right? So that means that roughly speaking, p plus q over 2 should be very close. This is a very close sign to the square root of n. If I get, a square from both sides. And that would be the only time that it happened that, if this thing is quite close to this thing, then I would have a smaller square over here. So the interesting thing is that I don't know p and q, but I know n, right? So all I can do is that I can start to guess. So this is going to be my test. And here would show us how we can actually factor this as number n if it has this scenario. So I can start to guess, let me call this one to be x. So I start x to be square root of n plus 1. And then I keep checking a square root of n plus 2, and then square root of n plus 3, and so on and so forth. And every time that I choose this x to be a square root of n plus 1 plus 2, and so on and so forth, I check whether x to the 2 minus n is a square. Right? That is the answer to my test. Look at here. From the above equation, the difference between these two values should be a square number, p minus q plus 2 to the power 2, right? So I get the I put both sides on the square, and then to the power a half. So what I get over here is that if this difference, if whatever x I get, I raise x to the power 2 minus n, if the result is a square, and if that is the case, in this case, we would have such a formula. x2 minus n equals to some, let's say, y square, right? Some small y. And then if I just move the thing around, I can show that x minus y and then x plus y equals to n, right? And that means that we can factor n and compute p and q. So it is a very tricky and very small thing, and everything is started off with this playing with P and Q, and the knowledge that the difference between P and Q is small, that help us to run this attack. Otherwise, if the difference is huge, then this test itself, we would have to run it for a lot of numbers, and then that for loop itself would become something that is computationally expensive. As long as P and Q are equal, then we know that the difference between P plus Q over 2 and N, the square root of N, are a small and a square, whatever difference they have. And since that is the case, I know that this equality should be very close to the square root of N. So I start to try some numbers around the square root of N, and hopefully after some small checks, I'll find out that when I choose one of these x's, then the result that I get over here, x to the 2, whatever number I get to the power 2, minus n, becomes another square. I don't know, for example, 4, 16, 81, whatever number, that is the square. And then if that is the case, then we already have enough information to factor or integer n. So this is the last thing that we wanted to discuss about the RSA. And you see that if this P and Q are not really carefully chosen, even though the factorization is hard, but we never said that the factorization is always hard. Generally, for majority of the numbers, factorization is a difficult task. We can't do factorization for every integer, but you see that there are some exceptions. And for these exceptions, we have some strong algorithms that if you don't choose your prime carefully, then we could easily run into these problems. So, it is, I hope that you're convinced now that, finding out these attacks or following them on the papers for every individual of you would be a difficult task. You're learning cryptography so that hopefully you would later use it in your job. So now you understand and appreciate this, community work, that a lot of open source libraries are out there. People are investing their time to make sure that they take care of all these small things that show up in their research. And, you have some sort of a strong and resilient library against this sort of attacks that are known, that are already published out there. All right, so that was it about our RSA algorithm. We explored the RSA signature. We also saw that we can use the hash functions. So today would be a day that we would explore a lot more about hash function. We would formally define it and see how it works. But the last thing to close down the loop on RSA is that so the RSA algorithm that we have learned so far, it has still many drawbacks, and it still is vulnerable against CCA attack. So today we will discuss one of the ways to protect RSA against CCA attack and some other vulnerabilities. So before I start this processing of the messages for RSA, I would like to also point out another issue with the RSA. So that, let me change my color. RSA is a deterministic encryption algorithm. Does anyone know what does this statement mean? Any clue? So we are saying that RSA is a deterministic algorithm. Anyone wants to guess what does that mean, or anyone knows actually what does that mean?
I don't know, but it sounds deterministic. Sounds like it has an endpoint, a conversions point or something of sorts.
No, we are not talking about. So let me give you the definition. We have basically two types of algorithms in computer science. If you want to see from one perspective. Some of them are deterministic, that for the same input, they always output the same. Then we have other algorithms that we call them randomized algorithms, that for the same input, they also get another input, which is some random source, random bits. And then every time that you call these algorithms for the same input, but with a different randomization, you will get different answers. That randomization, random seed or random variable, whatever you call it, you pass it to this algorithm. You can imagine that this algorithm is like walking to left and right, depending on the beat of the randomness that you provide based on the input. That would tell the algorithm to which, maybe in the beginning turn to left, right, and so on and so forth, make those random decisions. But when we are talking about here about the RSA, yeah, this student is also giving a very good answer. So it would always generate the same output. So let's look at the encryption algorithm. So the encryption, oops, what is happening with my pen? Oh, perfect. Okay, wow, I have many of them. Encryption of a message given the public key with the RSA, we get m to the e mod n, right? I know the public key and I know how the encryption algorithm works. So every time that you pass the same message, the resulting ciphertext would be the same. There is no randomness here. So one of the problems for such a deterministic algorithm is that when I know somebody's public key, I can go ahead and create a table, given PK, right? I can generate a pre-computed table. So let's say I see that what is the encryption of message 2, what is the ciphertext of 2, and then I choose the message to be 3. I pre-compute the ciphertext of 3, and choose 4, and C4, and so on and so forth, right? So I can go ahead and pre-compute this one. And once I have pre-computed this table, then when somebody's sending a message to this user under this public key, I go and do a table lookup. And if any of those ciphertexts appear to, there's a matching here, then I know that what is the corresponding message on that ciphertext, right? So that is a big problem. It is a big problem. We are kind of not worried about it much at the same time. The reason is because the message space in RSA is gigantic. It is like, it will cover like a huge range of numbers. So even though somebody devotes a lot of space, a space in a hard disk drive and computational power, you won't be able to go through the entire even you can pre-compute a significant portion of this entire set of messages. But it doesn't mean that you cannot cover anything, right? So you can start to run your laptop for a day or two, a month, and then try to pre-compute some of those values. And in some cases, you might get some success, get to know the value of the corresponding ciphertext. So this is an issue. You need to address this one. And also another issue that we've just discussed, that the algorithm itself is not CCA secure. So, as soon as we provide decryption oracle to the attacker can immediately break the RSA. So the purpose of this slide in this page is to explore the way that we can fix this issue. And then for the case of RSA, the message padding has become a very good practice. There are many versions of this padding, and today we would explore one of them. And then there are other versions out there that I think after learning this one, you will get enough background so that you can go and explore the other versions as well. So the idea is to add a padding and to the message and somehow make the message randomized. That sounds a bit odd, but bear with me that you will see that how this can actually really help to protect the RSA. So the name of the algorithm is OAEP. It stands for Optimal Asymmetric Encryption Padding. So if you look into the internet, you will find different versions of this. But for the purpose of this class, we would start with the basic version so that you get the whole idea in a simplistic way. So the algorithm starts with just defining two new things. We need to have a function g that takes k bits input, and then over here, and then it would output l bits. So whatever k bit you pass into this function, it would output l bits. So it is a pseudo-random number generator. So in this example, k is less than l, right? Because you use getting a smaller number of bits and generating to a larger one. We also have a hash function at the same time that gets l bits as input, and it would output or shrink them to k bits, right? So it does the opposite. But the hash function, remember, is not a pseudo-random number generator. It happened that, for this example, the size of their domain and their range are the opposite of each other. There are two different objects with two different purposes. So the idea is to pad a message M before we even encrypt it. So let's see how it works. Before starting anything, we suppose that our message is L bit. So remember, you see that we all using some parameters over here. Depending on your setup of your RSA key generation, you can decide about these numbers. These are just a parameter that we would add them to our key generation algorithm. It would make it a little bit more complicated, but it is something that is not super complicated. We should be able to do this one with no problem. So we assume that our message is at most L bits, right? So this is the restriction that we would have on the M. And then after we pad our message M that we denoted as X, X is K plus L bits, right? So it means that our N of RSA should accept the messages that are K plus L bits. But our actual message that we want to encrypt are a little bit smaller. So before we get there, let me go through a better explanation of my version. So we are talking about two operations over here. So we want to do encryption and at the same time decryption. So for the encryption, we need to take some steps before we move forward. After we modify our public key generation because of this new requirement, our public key of RSA is going to look like the same E. We have N, and also we have to add this extra information that we are going to do N, K, and then the function G, and then the hash function H. We need to give this pseudo-random number generator G and a hash function explicitly into our public key, because whoever is going to send the encrypted message to this user, they're gonna need this exact functions so that the recipient would be able to decrypt it. So we need to provide them in our public key to be very concrete. So the way that we are going to pre-process a message before encryption is as following. So the first thing first that we want to do, we are going to choose a random string. random string R that is k bits, right? Oops. It has to be exactly k bits. So that is the step number 1. We choose a key and we make sure that we choose a R random, bits, and we have to make sure that it has exactly k bits. And then 2, we are going to pad our message. So the padding of message, you said that is going to be equal to X. Let me write it, then we will discuss it. So we're gonna take M, we XOR M with the G of R, and then concatenate this one, R XOR with hash of M, XOR with all right, which is equals to, okay. So the first thing first, this symbol, if you have forgotten by any chance, is what we call it the concatenation. And this symbol again is nothing but just a XOR, right? So what it says is that you take the whenever you want to pad M, you take M, you XOR it with the G of R. We said that R is k bit, so our G function takes the input of k bits and it would output the L bit random value, right? Pseudo random value. And our message is also, we said that it has to be L bits. So you basically take our message and then you randomize it, when you XOR it with some pseudo random value, we randomize our M based on this output of the G function. And you see that every time that we want to do this padding, we choose a different R. So every time that you are going to encrypt our message, we are going to choose a different R, and therefore this value G of R would change, and therefore always this first part would change, right? So now you could see that every time that you're going to even encrypt the same message with the RSA encryption now, the value of the X would be different, even though we are passing the same M, and that's depending on some other random variables that we have over here. And also at the same time, we are you see that we are adding extra information to it. So that was it. So this is going to be L bit, and then we are also going to add some extra other information. So let me just make some variable names over here. So I'm gonna recall this one to be A, and then this whole thing over here, this whole thing, I'm gonna call it B, right? So notice that you see M XOR with GR inside this hash function. So inside here is again A, right? So just different representation. So I'm gonna say that after I do this padding, what I get is A XORed with R concatenated with R XOR with hash of A, right? So I can write it this way, and we call this whole thing B, right? So at the end, when we do all this computation, we have A concatenated with B, so we just write them together. But if you look inside B, you see that we are doing over here, we are computing hash of A itself, just like what we have here, and then we add we XOR it with R. So remember that our hash function is the output is k-bit, and then our R happened to be also k-bit. So when we XOR them together, we are XORing two k-bit strings to each other. So far interesting. So look like we add some stuff and we randomize the message. So now we can compute or encryption function. So encryption of on X and with a public key, and that is going to be your C. So the way that it works is that for RSA, is going to be x to the e mod n. No more m. We are encrypting x mod e, to the power e mod n, right? After we add these things. So I think it's a little bit confusing until we get to the decryption part, that you see that we are able to recover m. So bear with me for these two steps, and then you will see that this would actually work. So in order to decrypt, we need to take two steps. Number one, of course, we need to decrypt it. So we need to compute the inverse of, we need to compute the decryption of C and the public key, which is going to be C to the power D mod n, which is going to be x, right? And we know that by definition, x is actually equals to some a and then concatenated with b, right? How do we know that? We want to take the first L bits to be a, and then the rest of them, which are going to be k bits, are b, right? That's how we would separate them. When you see, then you get the x, you collect the first L bits, and then you would treat them as a, and then the rest of them, which should be k bits, we are going to treat them as b. Now that we got that, so now let's see how the magic happens. We are going to set R to be hash of a and then XOR with b. Let's see how that works. In order to recover m, we are going to need this R, but at no point we send R to the recipient. But the point is we can recover R the way that we have orchestrated this formula. So I'm saying that R equals to the hash of A XORed with B. How do I know that? Because I know the exact hash function that they've used. So hash of A is going to be the hash of this first L bits. So it's going to be exactly, actually hash of this value over here. So it's going to be hash of M XOR with G of R, right? So this is actually what happens if you compute the hash of A. And what was B? The B was the rest of them, this K bits. And if I write down over here, it's going to be, if I XOR this one with B, B is R, and then itself is XOR with hash of M XOR with GR, right? All right. So the interesting thing over here is that when you XOR two values, the result would cancel each other. So you see that we have a hash of M XOR with GR, and again hash of M XOR with GR. So these two things would get cancel each other, and the result is going to be just R, right? That is what is remaining. So now we have recovered R from there. So now that we have recovered R, I'm going to say that M equals to A XOR with G of R. So what was the M? A was M XOR by G of R. If I XOR A with another J of R, again would get canceled and I recover J of R, right? Now I know R, so of course I can compute this one. So this whole thing equals to M XOR with G of R, and then we XOR it again with G of R to cancel it. And you've seen that this two would also get canceled, and of course we would recover M. That's exactly what we were looking for. And there we go. So the whole interesting thing happened because of the way that we have formulated the things over here on formula line 2, step 2. it is a very clever way to, randomize M, and also this extra information that we put over here on B would help the recipient to recover R, which we would need it to recover the actual message from X. So now if you follow this algorithm, so let's say you want to encrypt a constant message 2, let's say my message is integer 2, and every time that I run this encryption algorithm now, I modify the encryption algorithm. Every time I would choose a different R, right? And every time that I choose a different R, therefore X would be different. And when X is different, therefore C is different. The rest is deterministic. When X is a different, so C is for sure different. So if somebody now sitting on a line like Eve and sniffing the line and try to find those messages and match it to the table, then Eve wouldn't be successful because we are randomizing these values. Eve wouldn't be able to decrypt it, of course, and as long as he can't decrypt it, recover the R, he wouldn't really know what is the corresponding message within this value stands for. And it's interesting, even though somebody sent 2 ciphertexts. Let's say I encrypt and send 2 ciphertexts that happen to be the same, for this user. You can't really conclude that I'm even encrypting the same messages. It could be 2 different messages, but because I'm choosing different R, their decryption could be the same. So, but that is a very interesting property that we are adding to RSA. So going back to the top, so we have a proof that we won't go through the proof that RSA, when we add this padding to the RSA, we call it OAEP, is proven to be secure against adaptively chosen ciphertext attack, the attack that we discovered on the previous page under random oracle model. So we would get back to this random oracle model very soon. You'll see an example. Why do we need to have a random oracle model? Sometimes for the security proof of some crypto systems, we have to use random oracle model, and you will see an example very soon for yourself and discover why do we have to have that. All right. Any questions?
From the public key on the top, can you point to which of this, the E, the N, the L, K, G, H, from this public key? Not every value of those. It's known. Like, what's public here? The N for sure.
No, this is the public key. Everything is public here.
Everything is public.
Yeah.
The L,
So
the
the
K.
secret key is only the D, the exponent D that this user didn't publish. So what hash function I use, to encrypt for this user, what pseudo-random number generator you should use, what is the maximum length of the message that you can encrypt for this user, what is the length of the random R that you should use, all of them are public information. If you don't have this 4 new piece of information, then you are not able to encrypt anything for this user.
Okay. And the only thing that makes it secure is that they don't know the D. Okay, super.
Yeah. So the knowledge of this L, K, G, and H doesn't help anyone. It's just like public algorithm, different algorithms. For example, I tell you that I use SHA-1 or MD5. I use whatever different pseudo-random number generator. That doesn't help you to break RSA. Those are just different algorithms that I chose. But I need to tell you, because you see the steps, and for the encryption and decryption, because I'm going to use those hash functions, we need to use the same functions, right? Those are the deterministic algorithms. So we need to make sure that we are, agreed that when you send a message to me, what algorithm you're going to use.
Okay, and when you talk about the oracle, that's like a proof of concept thing, right? Oracles are not an actual thing, or
yeah, they do not exist. Okay. But in the theory, sometimes we want to prove, we have to use. Sometimes we assume that For example, very soon we would prove RSA signature scheme, and then for that I'll use a hash oracle. That hash oracle, I assume that the output of the hash functions are uniform random. Such a hash function doesn't exist, but in order for me to prove, I need to have that assumption. So I instantiate my assumption in theory with the hash with the oracle. But I mean, soon you will see how does that work. We have a very good example for that. Right. Okay. All right. So it's close to your break time. There is one more thing to discuss about it, and I think we won't be able to do it. So let's take a 10 minutes break, and then we come back and we continue.